let's start talking about one of those types of waves that you encounter pretty much all the time. Even if your eyes are closed, you just are going to detect sound waves. We can't close our ears too easily, so we're always kind of stuck with these. So what is it about sound that is wave-like? How do we measure the wave-like properties of sound? And keep in mind, as we had discussed earlier, that sound, is a longitudinal wave. And if I have a wave that is going, let's say, left to right, like you see in the arrow on the screen, then what happens is the air along the length of that path of propagation, if I take a snapshot, we're going to see some parts of the air where the molecules are concentrated, alternating with regions where there is a relative paucity of air molecules. And where we have excess air molecules, that would be a region of compression, and where we have a relative lack of air molecules, we would have a rarefaction. And so we have alternating regions of compression and rarefaction as we look down the length of a longitudinal wave. In this animation, we can think of that longitudinal wave traveling left to right. And the small circles that you see are what's happening to the air molecules. They basically oscillate back and forth in a direction parallel to the direction of the wave's propagation. There are times where a pair of small circles are very close to each other, and in those locations, those small circles represent a compression. At the same time, two small circles are close to each other, they are relatively far away from the next pair of small circles. And midway between one pair of small circles and the next pair of small circles, we have a rarefaction. Also, there are times in which these air molecules are roughly equidistant from each other. Again, we're talking about instants in time. At those instants in time, there is neither compression nor rarefaction. This is a phenomenon that is always oscillating from one extreme to another extreme. If we plot the deviation in pressure from atmospheric pressure, then we get a sinusoidal function. So on the screen, you see a graph. The vertical axis is delta P. Delta P is the pressure at some location X minus the average pressure. So where you see delta P equals 0, where the curve crosses delta P equals 0, at that location in this snapshot of time, the particles are at atmospheric pressure. But where you see a positive peak at that instant in time, the particles are at higher pressure because they're compressed. And at the bottoms of these oscillations, the particles are relatively more widely separated from each other. The pressure deviation is negative, and we have a rarefaction at that location. Because the behavior is sinusoidal, I can use a sine function to represent the wave behavior as it depends upon both location x and time t. The amplitude of the pressure deviation is delta P max, and my expression for pressure deviation as a function of x and t is delta P max times the sine of kx minus omega t. But an alternate way of looking at the sinusoidal behavior is to consider how far the molecules are from their equilibrium position. And we can call that S. And there is a maximum deviation of these particles from equilibrium. We'll call that S max. And for a function of location x and time t, I can use a sine function to describe the location of these air particles, S max times the sine of kx minus omega t. Sound through a material has a speed. What that speed is depends upon the material, and more specifically on two properties of the material. One of those properties is the density. Now, if we're talking about something like air, the density can vary. It's not at a fixed value. But another property is something called bulk modulus. Bulk modulus is a measure of how hard a substance is to compress. If I take a balloon and I fill it with a gas, if the gas is really hard to compress, then what we have is a gas with a very high bulk modulus. Solids and liquids tend to have extremely high values for the bulk modulus, whereas gases tend to have relatively low values for the bulk modulus. And what we find is that the speed of sound is equal to the square root of bulk modulus divided by rho. As far as the units are concerned, rho has units of kilograms per cubic meter in standard units. Bulk modulus actually has units of pressure. So as I hope you got from my previous discussion, I can look at the speed of sound in things other than air. I can look at the speed of sound in solids. I can look at the speed of sound in liquids. I can look at the speed of sound in the interstellar medium. That's what you see on the right-hand side, an example of sound in space. You might say, well, in space is a vacuum. It's not a perfect vacuum. There is a lot of dust, a lot of gas out in space. It just happens to be much less dense than what you find on the Earth. But it is out there, and it is possible for sound to travel through space. And so you see on the graphic to the right an image of where there seems to be a black hole at the very center, and you see concentric rings that are actually the result of sound waves. These are waves that have immensely long wavelengths and immensely small frequencies. The sound waves here have some of the lowest pitched sounds in the universe, way lower in pitch than you could ever imagine. Let's take a look at an example of calculating the speed of sound in a solid. What is the speed of sound in gold? We need to know some properties about gold. Being a solid, the density of gold is pretty well fixed, and we can look it up. It's 19,300 kilograms per cubic meter. That makes it quite a bit more dense than even lead. We also need to know the bulk modulus of gold, and you can look it up in a table, and you'll see something pretty close to 220 gigapascals. Now, because giga is not going to be standard, we have to convert our measurement to standard units. Giga means times 10 to the 9. The bulk modulus is 220 times 10 to the 9 pascals. It is now in standard units. Plug it into the formula. The square root of the bulk modulus divided by the density rho. 3,376 meters per second. Is this reasonable? It's about 10 times the speed of sound in air. But for a solid, that is a perfectly ordinary value for the speed of sound. Take a look at the table on the screen. For 4 different substances, you are provided with the value of the bulk modulus and the density, and you're asked to identify which one has the highest speed of sound. Now, you might think you have to dig out your calculator, but you can actually solve this without your calculator. Think about it. Square root of bulk modulus in the numerator, density in the denominator. See if you can come up with the answer without using your calculator and determining all of the different speeds of sound. If you're in a large volume like air, and I hope you are in a large volume like air, using the bulk modulus is pretty good. There's no particular direction in which you have a lot more air than another direction. You have as much air to the left as to the right, forward to back, front and down. That's not always true for, say, solids. Solids are often shaped into a thin, long configuration, a long, thin rod. And because of the fact that there is one dimension that is kind of preferred compared to the other two, there is a better expression to calculate the speed of sound. So if I have a bulk solid, I'll use the bulk modulus over rho and take the square root. But if that solid is shaped into a long, thin rod, then I want a one-dimensional measure of how stretchy or compressible that solid is. And that one-dimensional measure is called Young's modulus. And it's represented by a capital Y. And in the case of a solid being in a long, thin rod, we would express the speed of sound as the square root of Young's modulus divided by rho. So, by the way, if you have, say, a long, thin solid like a ruler, and let's say you have this ruler in front of you, if you just tap one side of the ruler, say to the right, you just tap it, does the far end of the ruler from the tap move literally instantaneously? And the answer is no. The shock wave created by your tap on one side has to travel down the length of the ruler, and it's going to travel at the speed of sound in that solid. In a previous lecture, when we generically discussed the relationship between intensity and amplitude, we said intensity is proportional to the square of the amplitude. That's true for sound waves, but now we're going to look at the explicit relationship between intensity and the square of the amplitude. If we are talking about the amplitude as the deviation in pressure, then I get that the intensity of the sound, capital I, is equal to the square of the amplitude of the deviation in pressure divided by 2 times the density times the speed of sound. There is also a proportionality between the maximum pressure deviation and the maximum displacement of the air molecules as they oscillate back and forth. And that maximum, the maximum deviation in pressure is equal to the angular frequency omega times the wave speed v times the density of the medium rho times the maximum displacement S max. So 2 equations here that apply to sound, one that shows the relationship between the maximum deviation in pressure and the maximum oscillations back and forth of the air molecules, and one that shows the relationship between the intensity and the maximum deviation. So these apply to sound alone. Let's do an example. What is the maximum displacement of an air molecule if you are listening to the softest hearable sound? Now, this is a very open-ended question because it doesn't give you any numbers. So we're going to, for purposes of this question, pick out a few numbers. The first number we'll pick out is the frequency of the sound. We'll call it 1,000 hertz. This is a bit higher than even a baby's cry, but not dramatically higher. We also need to know what is the intensity of the softest possible sound that a person can hear. Well, we're going to look at the average person with healthy ears, and the softest possible sound has an intensity of 10 to the negative 12 watts per square meter. We also are going to pick the density of air to be 1.20 kilograms per cubic meter, and the speed of sound in air as 340 meters per second. If this were a test question, I'd have to give you these values. We want to find S max. If I find delta P max, we have a formula on the previous slide that allows us to determine S max. Well, if I want to find delta P max, I have information using intensity, so I'm going to have to use that first equation on the previous slide. If I take that first equation on the previous slide and I algebraically solve for delta P max, I get that it's equal to the square root of 2 times rho times V times I. I know rho, I know V, I know I. We plug in the numbers and we get that the maximum deviation in pressure is 2.86 times 10 to the negative 5 pascals. That's actually a very small deviation when you consider that atmospheric pressure is on the order of 10 to the plus 5 pascals. This deviation is only about 1/10,000,000th that of atmospheric pressure. So it's obviously, on the scale of things, extremely small. Yet we can still just hear it. But how does this pressure deviation translate into a maximum back and forth oscillation of a molecule? We plug into our formula for S max, and if we solve for S max, we get that it's equal to delta P max divided by omega times V times rho. Omega is equal to 2 pi times the frequency. We were given F. 1,000 hertz tells me F. So 2 pi F gives me omega. V is 340. Rho, we picked 1.20. Those are in standard units. Plug in the numbers, and we get that S max, the maximum oscillation of the air molecule from its equilibrium position, is 1.11 times 10 to the negative 11 meters. This is about the size of a single hydrogen atom. So this back and forth oscillation is not microscopically tiny, it's more like nanoscopically tiny, and even that's too big. We're talking more about picoscopically tiny. That's how small it is. And yet, we are still just able to hear that little back and forth banging against our eardrum. When you talk about sound, though, you don't normally talk about intensity. In everyday conversation, if you talk about the loudness of sound, you're going to talk about the decibel. What's the decibel, and how does that relate to this conversation? The decibel is a logarithmic calculation. It's a logarithmic calculation because our ears respond logarithmically to sound intensity. If the sound doubles in intensity, our hearing does not detect it as doubling in loudness. Our hearing does detect an increase in loudness, but that increase doesn't respond linearly. It responds logarithmically. So in other words, if the intensity increases in loudness by a factor of 10, what we actually hear is more like an increase of 10 decibels. So 20 decibels to 30 decibels represents the intensity actually growing by a factor of 10. The decibel is based on the softest possible sound a healthy human here can recognize. And that intensity is 1 times 10 to the negative 12 watts per square meter, as we discussed on the previous slide. To determine the number of decibels, you need to know the intensity, I. You take I, you divide it by 1 times 10 to the negative 12. You then got to dig out your calculator and use the logarithm function, specifically the base 10 function. Don't use the natural log ln. Use the log function log. Take the log of the result of that division, and then you have to multiply by 10 to get the number of decibels. The number of decibels, sadly, is sometimes referred to as the intensity level. So pay attention. Is the problem asking for intensity, or is it asking for intensity level? If it's asking for intensity, you're looking at watts per square meter. If it's intensity level, you're looking at decibels. Intensity level, when it is a variable, they sometimes use the lowercase Greek letter beta, which is kind of the funky-looking B you see on the screen. Lowercase Greek letter beta represents the number of decibels. It is the intensity level. Because of the way the number of decibels is defined, if you are someone whose hearing is healthy and more acute than average, you can hear negative decibels. Nothing wrong with that. Just means you have good hearing. It is also the case that different frequencies, even if they're played at the same intensity by a machine, some frequencies will sound louder than others. That's something that we're going to get into later, but some frequencies are heard by human ears more easily than other frequencies, and we'll see why as we go through these lectures. On the flip side, from the softest possible sound, the loudest sound in air ever recorded was on August 27th, 1883. The infamous volcano Krakatoa basically exploded. And the people who were 40 miles away at the time it erupted, their eardrums were completely ruptured. 100 miles away, the number of decibels was 172, which is louder than being next to a jet engine. People 3,000 miles away could hear a rumble. That's like making a sound in Harrisonburg and having people in LA go, "What was that?" Let's do some calculations. Suppose we have a 90-watt speaker. It emits sound isotropically. What if someone is 2 meters away? What intensity level do they detect? How many decibels? Compare 2 meters away with 25 meters away. What's the intensity level when you're 25 meters away? Because the sound is emitting uniformly in all directions, because it's isotropic, we can calculate the intensity as power output divided by 4 pi r squared. For someone 2 meters away, r is 2. 90 divided by 4 pi times 2 squared. The intensity is 1.79 watts per square meter. Let's find the number of decibels. Beta, the number of decibels, is equal to 10 times the log base 10 of 1.79 divided by 10 to the negative 12. Take 1.79 divided by 10 to the negative 12. Take the log of that result, multiply by 10. I hope you get 123. Intensity level is 123 decibels. What if they're 25 meters away? It's the same calculation, except now R equals 25, and we get an intensity of 0.01146 watts per square meter, and a resulting intensity level of 101 decibels. So the second person is just over 10 times farther away than the first person. The intensity level has dropped by, the intensity has dropped by a factor of about 100, from 1.79 to 0.01146. And yet the number of decibels drops by only about 20. Is that loud? Is that reasonable? You don't want to spend too much time 2 meters away from a 90-watt speaker. 120 decibels is generally the point at which people start to feel pain from the sound. And even just exposing yourself to 100 decibels long enough is going to permanently damage your ears. So you have to be careful about that. Just ask any 70-year-old rock star. That's enough for now. Bye-bye.